Okay, so let's work Pathways Problem 2.40 from the textbook. It reads, chlorine has two isotopes, chlorine-35 and chlorine-37. What is the mass number and how many subatomic particles are present in each of these atoms, or one atom of each type, okay? So this is a pretty straightforward problem, but it's a skill that each student in chemistry needs to know, okay? It's pretty basic stuff, and you're reasonably likely to see a problem or two like this on the exam. This is the type of problem that's really easy to throw in, okay? And it's really simple, so I want each and every student in my class to get this correct. The thing that you need to know, or the key bit of information, is how we keep track of all this. It's usually done through a notation that looks like this, okay? Or the capital X is the elemental symbol, much like chlorine is the elemental symbol here, okay? Now, to the left of the element symbol, there are frequently two numbers. So there has to be at least one written, but there's frequently two. Sometimes you can figure out the other just by knowing what the element is, okay? But the one that's an absolute must is written as a superscript to the left of the element symbol. That's known as the mass number. See the number 35 and 37, they're written slightly above. That's called a superscript. Those numbers, 35 and 37, are these mass numbers. So actually we're already starting to answer the problem. Those are our mass numbers for each of these isotopes, okay? Different isotopes of chlorine. That's a must. Now below that, we write the atomic number. That's given the symbol Z. We can write it there. You don't have to write it, turns out, because it's a little bit redundant. And the reason why that is because all atoms of chlorine, if it's chlorine, 35, 37, some other isotope, it doesn't matter. All atoms of chlorine will have the exact same atomic number. That's the number of protons that's in the atom's nucleus. That is the same for every single atom of chlorine. If it's chlorine, it has a very specific number of protons in the nucleus. Now, another thing that you might see in these notations is to the right of the element symbol. It's written as a superscript, or slightly above the midpoint of the element symbol. This is where the charge on the particular substance goes. Sometimes it's +1, -1, +2, -2. It can take on different values. It can also be neutral or zero charge. Now, looking at the fact that I don't have anything written here in my problem, nor do I have anything written as a superscript here, both of these substances are said to be neutral. Okay? If there's nothing written, you can just assume it's neutral. So there's no charge on these particular atoms. It'll make our life a little bit easier when we go to figure out how many particles must be present. So let's dive into that. We know the mass numbers are 35 and 37, respectively. So we're pretty much done with that first part. That was very easy. But we also want to know how many subatomic particles are present in each. And this isn't terribly difficult, but at least it's a little bit more difficult than the first part. So I'm going to have two sides, one for chlorine-35 and the other for chlorine-37. And we're going to work through this, all right? Now you may remember there are three different subatomic particles that make up our atoms. There are protons, there are neutrons, there are electrons. Three different particles. We want to figure out how many of these are present given this notation. How do we do that? Let's start with protons. Now, if you're given a value for Z as the subscript in front of the element symbol, that number is consistent with how many protons. So if I was given a number here, I just have to take what it was and plug it in there, and I'd be done. But there's another way to figure out how many protons are present. I mentioned earlier that the number of protons which are present in the nucleus of the atom defines what that atom is. Now, if I go to my periodic table of the elements, and I look up the box for chlorine, which is, you may not be able to see this, but it's right over here, okay? Chlorine's atomic number is 17. This means is that every single atom of chlorine that has ever existed has 17 protons in the nucleus. That's what makes it chlorine. It's by definition what makes it chlorine. So I can also write 17 protons over there. That's the atomic number. That's the integer number that's in the box on the periodic table. Number of protons in the atom's nucleus. Now the next one's at least a little bit harder. Number of neutrons. How do I figure that out? Well, it turns out that this number that's written in front of the element symbol is really important for this. Remember, this one's called what? The mass number. The mass number. It just so happens that the mass number is equal to the number of protons plus the number of neutrons. Okay, mass number is protons plus neutrons. So if my mass number is 35 for this particular isotope of chlorine, and I know that I've got 17 protons, because that's what makes it chlorine, then I have to find the number that makes this equality work. It's almost like having algebraic variable x here. X plus 17 has to equal 35, because that's the definition of mass number. So it doesn't take very long to figure out that there must be 18 neutrons in that nucleus. So 17 protons, 18 neutrons, that makes 35. That gives me my mass number of 35 while allowing my atom to be chlorine. Now what about electrons? Notice there is no charge here. No charge at all, right? What that tells me that this atom must have 17 electrons associated with it. Because what particles are our charge carriers in our atom? Remember, the protons are +1 each. The electrons are -1 each. So if I'm going to have a net neutral, where there's no excess positives or no excess negatives, these two, the protons and the electrons, have to be in balance. The neutrons are neutral, so they just kind of stay out of this discussion of charge, right? But if I'm going to have a neutral atom, protons and electrons have to balance each other out. So if I have 17 protons, I must also have 17 electrons to get my neutral atom. Alright, so let's finish off this same problem over here on the right for the other isotope. I hope this is all making sense for you, because this is pretty simple stuff. Everybody needs to get this right though, okay? Now what about chlorine-37 isotope? So chlorine-37, how does that say that one? This is chlorine-35, okay? Now, it's got 17 protons because it's still chlorine, and every isotope of chlorine has 17 protons. That's what makes it chlorine. Neutrons. Well, the mass numbers change now, but remember, the mass number is always protons plus neutrons. Now, I'm no longer dealing with 35, now I'm dealing with 37. I have 37 equals 17 plus number of neutrons. It looks like this particular isotope of chlorine, it's got 20 neutrons associated with it. And then lastly, since I don't have any charge, I must also have 17 electrons present in this particular atom. Now, just for a bonus problem here, what if I was doing this and it wasn't chlorine neutral, but it was chlorine -1? How many electrons would I have then? Well, to make that work, I'd have 18 electrons. One more electron than proton. One more negative charge than positive charge. And that would yield a net -1 charge for the aggregate, right? What if I had chlorine +1? This one's even more tricky. But it's important to realize this, okay? If I have chlorine +1, you may have been tempted to say, oh, I'm just going to increase the protons by 1. Are you allowed to do that? Think about it for a second. You're not. If you change the number of protons, you change the element. And that's going to make this Fluorine symbol incorrect. If you're going to increase the element number by 1, you're going to change what it is, fundamentally. So when you're changing these positives and negatives, these ion charges, you may never change the number of protons, because if you do that, you change the substance. You're only allowed to change the number of electrons. If you have excess electrons, this will be a negative charge. If you have a deficiency of electrons, say in this case 60, then you can still make the positive charge, right? Because you've got one more proton compared to electrons. So you have a positive 1 net charge. But what's important is I didn't change my protons. I've only changed the number of electrons. And in general, when dealing with the charges, this is what you do. You change the number of electrons to make the net charge work out. Okay?